Okay, hello everyone, and welcome to the Convex community call. Today we've got a super exciting topic, especially for the data geeks out there. We're talking about the data lattice and convergent storage, which is a super important topic, which is very much related to what we're doing at Convex. But also, I think it's a broader topic because I think the question about what is data, how do we manage it, how do we store it? How do we transmit it? How do we ensure its integrity? How do we make sure it's properly governed? Is a much broader topic, and I'm hoping in this discussion we can sort of touch on some of these things and how they relate to the Convex protocol and ecosystem, and how we actually make everything work behind the scenes, so that we have a sort of consistent story for everything we do about data and storage. Um, so. Um, First off, I mean, maybe just to recap a little bit about the Convex, about the way that the Convex works, is of course Convex is a system uh, for economics. It's for building economic constructs, different kinds of digital assets, different kinds of smart contracts, different kinds of economic systems that are open and accessible to everyone. And in that sense, it's all about data. It's all about managing data. It's all about what data represents the assets, what data represents the balances of people's assets. It's also about code. So in some sense, code is data. Code itself can be represented as data. Indeed, you have to represent it as data if you're going to transfer it around and let other people run it and let other people verify that code. So all the smart contracts are data as well. And the consensus algorithm itself that ensures that we get global agreement on the convex network is also data. That's just data which needs to be agreed by the peers on the network. And when we think about the kind of data that's getting managed, well, there's a very important piece of data, which is the global state, which is the data which is stored and managed by all the peers on the network. Everyone can see, and is sort of like the single source of truth for a lot of what goes on in Convex. So this is all the stuff like asset balances. It's all the stuff like public keys for cryptography. It's things like smart contracts, all the stuff that actually makes the Convex ecosystem operate. And that's all part of the global state, which is a very important piece of data which is managed by all the peers across the network using the convergent proof of stake consensus algorithm, which we've covered in other talks. But I think a very important point is that is only part of the story. That is a very important piece of data, the global state, and how that gets managed. But of course, applications require a lot more data and a lot more information than just the on-chain global state, which is managed by the consensus system. Applications are going to have media. They're going to have, maybe streaming videos. They're maybe going to have things like social media feeds with large numbers of posts. You might have your private documents. You might have a bunch of encrypted data. You might have a bunch of data which is sensitive, medical records that need to stay behind a firewall at all times. So it's never going to be the case that, or at least for more sophisticated applications, it's never going to be the case that you want to put all of your data on the Convex global state. So we very much designed Convex with the sort of the idea that you put in the global state what you need in order to make your economic systems work, in order to make identity management and governance work, and the smart contracts, obviously. But most of the data in most applications probably doesn't need to be part of the global state and probably shouldn't be part of the global state. Now, there's of course lots of ways of handling this. You can have an application which just talks to Convex and does the Convex bits with the global state, and then it can do everything else in very traditional ways. You can have standard Web 2 servers, you can have REST APIs, you can have all of these different systems that work in more traditional ways, and that's perfectly fine. But one of the things we always wanted in Convex was to say, well, okay, that's great, but maybe we can do something better, and that's led to the design of what we're calling the data lattice. And the data lattice is really a decentralized form of data storage, which allows applications to tap the power of a decentralized protocol and have data widely distributed and verified all around the world, but they don't have to put that data actually on chain. They don't actually have to do convex transactions in order to store that data. It actually is stored off chain from the perspective of the network. But it's still convenient to use some convex applications and still works in the same way, and it provides a sort of good solution to building decentralized apps using convex. So we've sort of got this sort of dual approach. We've got the global state, which is for, I guess, the sort of the contractual things that need to be managed by consensus, and you've got the data lattice, which is where you put all of your big data and the sort of large amounts of information that probably you don't want to put in the global state. And that's a good solution for what we call a hybrid application, or a hybrid DApp, because it can pick and choose which of those makes most sense for each particular kind of data. So that's the model. And of course, in a hybrid app, you can use convex global state, you can use the data lattice, and you can also still use your web services, your REST APIs, your content distribution services for streaming media, etc. You can really have this sort of open selection of using the best tool for the job, which is very much part of our philosophy. Yeah, it's how do you plug and play these different components to make the best possible solution. So as always, we'll be talking about these topics. Please feel free to fire away any questions on chat. I'll be keeping an eye on chat and sort of trying to answer any questions as and when they come up. Also, hopefully, doing a bit of a demo and showing you some of the sort of ideas and some of the sort of the things that we do in the sort of the data space in Convex, which are potentially interesting, both for people who are Convex users, but also people who are more generally interested in how we manage and control data and how we secure data. Couple of questions already. So what the store frameworks means for users and network sustainability? Well, great question. So for users shouldn't really need to know where the data is being stored. It should just work. But the advantage of the data lattice is, first of all, it's cheaper. Yeah, stuff on the data lattice, there's no transaction fees if you want to update data on the data lattice. You can run your own data lattice node and host your own data and not pay anyone else. So it's economically attractive to users. It can be faster. It can be lower latency. It can be sort of super high performance data access, and it can be as big as you want. Yeah, there's no limit to the size of the data lattice. It's effectively unlimited scalability. So you've got this incredible horizontal scalability of a decentralized storage network. So that should make things fast and cheap, which is ultimately things that users care about when they're using the application. And for network sustainability, I mean, it's a great question. I mean, first of all, it reduces the load on peers. Yeah, the fact that we don't have to put all this data in the global state makes the peers' jobs easier. So that helps for network sustainability and sustainability. Yeah, we don't want to bloat the global state. We have good solutions for managing the global state bloat, but we still don't want to put load on it, and we don't want people to be forced to use the global state when they don't need to. So it really helps with our sort of network scalability and sustainability when people use the data lattice, sort of assuming that's appropriate. So hopefully that sort of gives some of the motivation for why we're doing this. How does it relate to Oracle data? So I'm going to assume this means oracles as in oracles providing information to the network, as opposed to Oracle in terms of the software. So you can basically, an Oracle can be monitoring the data lattice and the global state, and if something happens, if it sees some data in the data lattice that it needs to put into the global state, then you can just have an Oracle. Yeah, so it can provide that data to a smart contract, for example. And that's an off-chain process, so you can have that running continuously and only notify the on-chain Oracle when you want to. So the data lattice can run completely independently of Convex. Yeah, but if you wanted to put the data into a smart contract, for example, that's when an Oracle would come in, and an Oracle would like relay some small amount of data and that would then trigger whatever needs to happen in a smart contract at that point. So that's completely application dependent, but that's the sort of typical way you might use it. Can I draw what these structures look like? Okay, this is a great question, and it's yeah, let's do some of that actually. So let me see if I can show some stuff just to sort of illustrate some of these things, and can I draw it? I mean, let's see. Have I got a good drawing tool? Can I do a paint thing here? Okay, this is going to completely stretch my skills. Okay, so let's see if we can do this. Okay, so what's a data structure look like? Well, they're all sort of basically going to be trees. Yeah, so we're going to have a node. We're going to have some nodes at the top of the tree, and then we're going to have a bunch of child nodes. And we're going to have a bunch of links between these nodes. Oops. Something like this. And you know, these trees can be as deep as they need to be. But basically, it's a kind of tree structure, and you've got some root at the top of the tree, and each of these things we call a cell in Convex. So a cell stores a smallish amount of data. Yeah, and you know, you think about a few bytes to a few hundred bytes to maybe a few K. Yeah, they're not big files. They're just, you know, small little chunks of data, and they contain, if you like, pointers to other cells. Yeah, and those pointers are references to the other cells that can be turned into cryptographic hashes. So this is actually what you call a Merkle tree, where every pointer in the tree is effectively a hash, so that it not only points to the child node using the hash as sort of as an index or a reference to the child node, but that hash can also be used to validate the integrity of the tree. Yeah. So if I was to make a change in this node here, then that would cause the hash to be changed here. And if you then tried to validate that at the top, you'd go, hang on, this hash has changed, therefore this data structure is not valid. So you can actually say that the entire structure is not correct. Yeah, and that model means that you can always validate the authenticity of one of these entire structures just by checking the hashes at each level in the tree. And that's a very important property, because that's what gives us authenticity and integrity of these data structures. All I need to give you is one hash of this top node, and you can validate the entire structure. Yeah, and that could be gigabytes, it could be terabytes of data, and you've just got these 32 bytes at the top, but you can validate that whole thing. And this is a very, very powerful approach. Yeah, this means that if you just put 32 bytes on chain on Convex, you can have a petabyte of storage of many thousands, millions of files, videos, whatever you want, and you can validate that all of that is correct and that there's good integrity on all of that data just by using 32 bytes of hash at the very top of this data structure. And that's the power of Merkle trees. Yeah. And it's a very important property which has shaped how we've designed the Convex itself, and also the sort of the data lattice technology which goes behind this. So I don't know if that helps, Riley, but you know, this just kind of illustrate, you know, what data looks like from a sort of graph perspective. Now, of course, there's another complete way of looking at the data, which is to say, okay, well, let's take a look at a sort of more of a sort of textual perspective. And some of you may have seen this app before. This is like our little Convex GUI, but I'm just going to go into this this screen here. It says message at the top. Really, this is for testing data structures and for looking at, okay, what is Convex data. And simplest thing is something like a number. Yeah, so I can just give it the number, let's say 7. Yeah, and what this tool does, it's a very handy tool. It takes the number, the data that I've entered here. It's turned that into an encoding. So we've got 1107 is actually the encoding of the number 7 in convex data structures, and it's taken that 1107 and it's done the hash, and it's come up with this 32-byte hash. So it told me the type, it's an integer, so 7 is an integer, that's useful to know. And then it's given me the hash. So that hash is 48B443C28, etc., etc. So that is the hash that you could use to validate this data. Yeah. So the number 7 will always turn into that particular hash on the data lattice or as part of Convex. Now, just to check we're not cheating, I'm going to take that 1107. I'm going to go into a web tool, so the SHA-3256 calculator. I didn't create this. This is just a totally standard web-based tool. I can put 1107 in here, and you can see I get exactly the same hash. Yeah, this 448BE hash. So we're just using completely standard cryptographic hash algorithms to do this calculation. So SHA-3256 is kind of one of the best-in-class hash functions. Very, very secure, very, very fast. It's kind of perfect for what we want. It always produces one of these 32-byte hashes, which is kind of super convenient. So we're just using the standard hash function. But whenever I say hash, it's one of these. Yeah, it's taking some bytes, some encoding of data, and it's running the hash algorithm on those bytes, and it's coming out with a cryptographic hash at the end of it. So that's 7. Now 7 isn't a particularly interesting piece of data. And the coding is actually quite simple. Yeah, so 11 is simply the tag byte that says this is a integer with a length of 1, one following byte, and it's going to say 07, which is the hex encoding of 7. Yeah, it's pretty simple. If I do 256 or something, then it's going to say, okay, that's an integer that needs 2 bytes because it's a slightly bigger integer, and its hex encoding is 100. So 16 times 16 is 256. So that's just a hex encoding of the data. Now it's actually kind of arbitrary length integers. Yeah. So as we make the integer bigger, it's going to get longer and longer. So one of the reasons we've designed this encoding system is it keeps common data structures very, very small. So very small in terms of number of bytes, which is important when you think about efficiency, when you think about network transmission costs, when you think about minimizing storage and of course performance. The smaller the data is, the faster things are likely to go, because this moving data around is on modern processors often the most expensive thing. So we want the data to be as small as possible. But any integer can be encoded, and that includes pretty big integers. Yeah. But notice that no matter how long the encoding gets, we're still going to get this 32-byte hash out at the end. So that's kind of it's always going to end up as 32 bytes once we've hashed it. That's just numbers, of course. Well, there's many other data types. So I can have a string. So I can put a string like hello in. That's got a encoding for the a string format, and if you know your ASCII, you can probably tell that these are ASCII characters, or no, UTF-8. So it's UTF-8 characters that get encoded in the encoding, but there's also a length of the string. So 30 says it's a string, and 5 is the length of the string. So five UTF-8 characters, and those then are the characters. So it's a very simple, compact coding format that's kind of logical, and it's designed to be as compact as possible. Now, of course, you don't just want these sort of single data items. Typically, you're going to want to create data structures. So I might have a vector where I put in several sub-elements. Yeah. So I can have a vector. I can add a bunch of different things in this vector. Let's put in a keyword, go to or something, And that entire vector, which has 5 elements, six elements, sorry, has been encoded into, again, an encoding. So that data gets encoded to this in hex, and then this is the hash that comes out at the end. So any kind of vector with as many elements as you want can be encoded. And one of the nice things about Convex is that the Convex data is kind of a superset of JSON. So any sort of JSON data, you know, name Mike, favorite color green or something. That's just sort of a JSON map with string keys, and that also gets encoded. Yeah, so anything that's in JSON format is very easy to encode in this in this scheme. And we can also, if this isn't enough, you can always encode whatever you like. Yeah, so I can just do some hexadecimal bytes, something like that, and that can also be encoded. So if you just want to put blobs of raw data that you know, can contain anything you want, any kind of format, you can do that as well. Yeah, and that also works in the sort of the convex data structures. So it's a very flexible sort of definition of data structures, which lets you include pretty much whatever you want. And these are all the sort of these are basically the things that are stored on the data lattice, and this is also the way that we represent data within Convex as Convex is running. So within the CVM and within the consensus algorithm, all data is basically following this model of being a tree of data with very, very efficient encoding. Now it's a little bit more complicated. When it gets loaded into memory, it sort of converts it into a slightly different layout of data in memory just for efficiency. But it's essentially, logically, it's always doing this. There's always sort of this idea of some pure information, and then how that information is encoded into something that then can be transmitted or stored. So, and then you can nest these things as much as you want. Yeah, so I can put vectors inside vectors. I can put strings inside vectors. Whatever. Yeah. Oops. It's telling me that I've not got the right number of brackets. There you are. Something like that. Yeah. So you can put in whatever data you want and structure it how you want. And this is really important, yeah, because different applications are going to require different structures. Maybe you want records with a fixed number of elements. Maybe you want, you know, these sort of lists of things that you can extend as far as you want. Maybe you have some kind of metadata format that you want to represent. Maybe you have different kinds of numbers or different kinds of schemas that you want to be able to encode. Because of the flexibility, you can pretty much do anything you're likely to want to do in a sensible application using these data types and this structure. And you can, as I say, you can nest them as deeply as you want. So you can have these very big data structures. And in fact, the entire convex global state, which can be, you know, gigabytes in size, is a single data structure. Yeah. And that's big. Yeah, they can be bigger than memory even. Yeah, because it's using smart loading and unloading of data under the hood. So it can actually be bigger than your computer's memory, and it's still going to work, which is very important as we start to get to, you know, the sort of the scalability questions in the long run. Well, these could potentially be very big databases, and the data lattice can be storing, you know, terabytes of data or petabytes of data, and we want to make sure that the entire thing is scalable to however large these data structures become. So you could take your entire disk file system and put it in one of these data structures if you want, and it would still all work sort of perfectly smoothly. Now, and then let's think about the kind of things you can do. So you could do a relational database. You could do tables in a relational database. You could do a graph database. You could do things like RDF triples and to sort of describe arbitrarily structured information, all of this as options using this format. So super flexible. It's probably more flexible than most programming languages have in terms of underlying data types. Okay, quick question. Can I explain the value of having the data in the data lattice instead of how other blockchains have to do it with IPFS or Arweave? So, I mean, good question. I mean, the data lattice does have some things in common with IPFS. IPFS does have this concept of having data which is addressed by hash. So this concept of content addressable storage. So we call it, the reason we call it content addressable, by the way, is because this is the content, this is the encoding of the data, and this hash is derived from the content. So the address for the content, which is the hash, it is derived from the content. So if you've got the content, you can figure out its address, and therefore you can address it. So it's content addressable. So IPFS is similar to some of the ideas of content addressability are very similar, and there's a bunch of other systems that use content addressability. It's a very powerful way of storing data because you don't have to remember the name of your content. You just provide that content, and you derive the name or the location of that content from the content itself. And one of the great powers of this is that it automatically deduplicates. Yeah. So if you insert the same content twice into a content addressable store like the data lattice, it only needs to store it once because we know from the cryptographic hash that it's the same content. Therefore, you just deduplicate. So we automatically deduplicate everything because of this property. So it's a very good way of handling addressing. Now, if you want to have other addressing and indexing, of course, you can build that on top. So you can build extra indexes if you want to give different kinds of addresses to the content. But the primary key, if you like, is the hash. So that's how it becomes content addressability, and that is similar to IPFS. I think what is different is convex data structures are really powerful fine-grained data structures, whereas IPF is more about storing big chunks of data, like blocks, like files. Yeah. Whereas we're thinking about down to a very fine-grained level. Almost the individual fields in a record are content addressable with the data lattice. Yeah. So we sort of push that to I'd say a different level in terms of granularity and the richness of the data types which is expressed in the system. So another question. So storing directly on chain will be expensive. I wouldn't say expensive, but you would have to pay transaction fees. And obviously, free any positive fee is worse than free. So it's a trade-off. Yeah, and obviously you can't really make this trade-off unless you know what the application needs. But if you don't need to put it on chain, you probably don't want to, I would say. So you put it on chain if you need other people to be able to verify it, or if it's needed for smart contracts, or if it's needed for on-chain governance, DAOs, this kind of thing, then you maybe put it on chain. But if it's something which doesn't need to be on chain, so for example a big image file, yeah, there's no point putting that on chain. Yeah, it doesn't need to be there. Yeah, and you might just want to put the hash on chain, and then then you can use the hash to look up the actual image itself from a content store from the data lattice. So that's the idea. The idea is we make it it's much cheaper and much more scalable to use the data lattice. On-chain is not going to be that expensive, but it won't be zero. So we want to, and we also want to discourage people from putting unnecessarily bloat on chain because that doesn't particularly help anyone. Yeah. So that's the kind of the model that we work on. Now we do have some quite clever tricks. So in Convex we have memory accounting, and what is beautiful about this is if you put some data on chain, but you go, whoops, I didn't really need to store that on chain, and I've just paid a bunch of fees for storing a megabyte of data, and I didn't really want to pay all of that. Yeah, and I want to be a good citizen. I don't want to bloat the on-chain storage. Then if you delete that data from the on-chain from the global state, you actually get your money back. Yeah, so we have a economic system which rewards people for cleaning up data on chain. So it's not all bad, and you can reverse it. Yeah, but it's still probably second best option, I'd say, for most apps would be to put data on chain. So you always first you want to see, well, can I do it with the data lattice, or can I do it with some other mechanism? So yeah, really awesome dedupe. So great for backups. So this is another fantastic thing about content addressable stores. Backups are really easy. Yeah, if you just copy the store, and you then you've just then got to back up everything. And if you want to reload it, you just push the same data back into some other store, or to some remote store or something like that. And you can't do any damage by putting the data in again because of the auto dedupe. Yeah, so it never does any harm to take multiple backups. You're never going to get any conflicts. You're never going to get any version issues. Sometimes when you try and merge databases, you get version conflicts, and they're really, really painful to resolve. I remember having to sort duplicate records out in SQL databases back in the day, and they were always some of the most painful things to debug and solve. The beauty is with this whole data lattice, all of those problems go away. It never hurts you to take backups, and it never hurts you to reinsert the same data, and you never get a conflict. And that's why we call it a lattice. It's conflict free. It's got this property of being a CRDT. So these stores are, they're replicable, and you can merge them at any time, and the merge is always going to be safe. So that's the beauty of the deduping and the content addressability, and the sort of treating it as a lattice. Another question. So you put on chain so the nodes back it up. If you keep it off chain, you have to trust someone or yourself to back it up. This is part of the trade-off. Yeah. So if you put it on chain, all the peers in the network are going to maintain it for you. So great. Yeah, that's fantastic. And it's great for reliability and all of that. However, it's only really you who cares about that data. If it's only you that, maybe it's a backup of your latest hit music track that you've been mixing, yeah, but not yet released, and you've encrypted it, yeah, so no one else can read it anyway. That kind of data, yes, you want a backup, but you don't need to have that backup publicly, globally visible to everyone or usable in smart contracts. It's just data storage. So Convex is the wrong kind of system to be doing backups of data that you are privately using. Yeah, it's not Dropbox or something like that. So this is what the data lattice is for. Yeah, the data lattice can replicate backups for you, and it can replicate this as much as you want. Yeah, and you can pay people to do that. Yeah, and you can create incentives for people to store things for you, and you can get people to stake indeed on are they keeping a valid copy of your data. So the way you do this is just using the hashes. Yeah, you say someone, will you keep this hash, this data for me, and here's its hash, and then to check whether they've actually kept it or not, you can always say, well, give me back the content, and prove that you can show some content that has that hash. And if they can't, they've failed to restore it, or they've failed to failed to reprovide the data on demand. So you can create an economic incentive for them to keep the backup, so that if you ever need to challenge the fact that they haven't got the backup, then they've got some economic loss if they can't produce the data. So you don't necessarily have, what I'm saying is you don't necessarily have to trust people, or you can pay a subscription and have a subscription service that backs up all of your data and just takes a dump of all your data and keeps it for as long as you want to pay for. So kind of like the equivalent of a Dropbox or this kind of thing. So, you know, I think one of the things about the storage is, look, someone's always got to pay for the storage infrastructure. Yeah, and yes, we want to make it cheap and efficient and scalable, but you know, someone's always got to store it, and someone's always got to absorb some cost for storing it. So again, it's an individual trade-off. If you just want to do the backups yourself and your local store and your local data lattice, you can. If you want to give them to a friend and say, hey, can you take this copy of my data lattice or my node at least, and just keep it, yeah, they can do that, and they can do that for you. And then if you ever need it back, you can just download the bits that you need. Or you could pay 20 people to do that, and just periodically check whether they've done it or not, and if any of them have failed, you send them some more, so you can do it in a more sort of informal, decentralized style where people just replicate stuff randomly, and no guarantees, but as long as you've got enough coverage and you check and you repair often enough, you can maintain a pretty high guarantee of that working. So there's levels of options, and different people would have different requirements. Some will want to pay for that service, some will want to do it with themselves or with a small group of collaborators. That's totally up to them. So we want to enable the choice, basically, of how the data lattice gets used most efficiently. Another point from chat: if the data lattice is decentralized, multiple nodes can run a data lattice node. Yeah, exactly. So anyone can run one of these, and they don't have to run a convex peer in order to run a data lattice node. So it's 100% free. Yeah, you just download the open source software, you run a node, put it on a server. You can use it locally. You can then access it from any. If you've got a port open, you can access it remotely. If you want to keep it private, you can also do that. And yeah, it's like RAID 5. It's like a replicated storage system where you just got to determine how many copies you want to have to be safe, and whether they're hot backups or code backups. You could put them on tape if you want. Yeah, I mean it's still just bytes. You can still restore them because it's all just pure content addressable stuff. So I mean let me do a quick bit of a sort of demo and of some of the tools and stuff. So I'll just and usual caveat, the API might change a bit as we evolve this, but this is just the command line interface. I've got my nice Windows PowerShell here. Can I make this a bit bigger? Yeah, make it a bit bigger. Okay. So what we have is we have Etch. So the Etch is the database that we use, and we actually use the same database for both. The convex peers use Etch as a database, but also it's the database that we use for data lattice nodes and for the convergent storage systems. So that's nice. It saves us a lot of pain by having this one sort of database format. I just do convex etch info, and it's just giving me a quick bit of information. So I have this etch file. It's in my home directory. It's in the sort of .convex subdirectory, and it's called etch.db. It's just a little file, single file database, so it's nice and convenient. You can copy it up and back it up easily, all of this kind of stuff. It's Etch version 1. It's got this data length. So data length is how much memory is being consumed in the file. It's got like 850k or something at the moment. So it's quite a small Etch database, but just for testing purposes. It's got this data root. So the data root is like the top of the tree that references all of the data that you want to preserve in Etch. That can be anything you want, but this would typically store, if you're running a peer, for example, that data root would store all of the global state and all of the consensus data that the peer needs in order to operate would be sort of included within that sort of tree, branching off from the root. The root memory size, so that's the actual size of the data, which is the logical size of the data. that comes off that route is something like 4 and a bit megabytes. And if you notice, this number is like 4.3 million, and that's about 0.85 million. It's a lot bigger. The actual size of the data structures being referenced in this little Etch database is about 5 times as big as the amount of storage that's being used on disk. Yeah, and that's because of the compression and deduplication. A lot of the data in here has been deduplicated, so even though we're technically referencing several megabytes of data, it's actually compressed all that down from deduplication to less than a megabyte, because some of that data is is just one copy is required. So that's the sort of the high level of what's at the top of this Etch database, if you just looked at it as the whole thing. If I wanted to actually see the real gory details, I could do Convex Etch dump, and this is going to produce a lot of stuff. Right, and it's filled my screen with data, but what this has basically done is produced CSV, comma separated values sort of file, and each of these lines, they're a bit too long, they're wrapping round, but each of these lines has a hash, which is 32 bytes at the beginning. It has a data type to say what that particular value is, which is kind of useful. So what's that data type? That 235 is the memory size, so the logical size of that data, and that, as I say, that can be bigger than the actual size of the data because it can be stuff can be deduplicated, and then the remainder of the line is the encoding of that data which is coming out of Etch. So in fact, this Etch dump, it's for diagnostic purposes and for searching and giving to other tools and stuff, but you can also use it for backup, because all you in fact need are these encodings, and you can then recreate the hash. The system knows what type it is and its length, because it can read that information from the encoding, so that just the encodings in fact are sufficient to back up the entire Etch store. Yeah, that's all you need. So if you just keep those encodings, you can always reproduce the database just by loading them in again. So that's the sort of data dump from Etch. If I want to actually read a specific thing, let's see if I can find something that looks like it might be interesting. Okay, this is an op. It says it's an op, so that's some actually convex code. There'll be some smart contract code in here, so I'm just going to copy that, and I'll do convex Etch read. Let's put that hash in. Yeah, okay, so this is some kind of token. This is a bit of code. This is a snippet of code from a global state, probably. And it's got, okay, so it's doing some convex balance. It's got a pool. It's got a token balance, calc rate. I suspect that's from the DEX. That's probably part of the Torus DEX. So one of the price calculations from the automated market maker or something like that. But that's actually code. That's convex code which has been stored in Etch with that hash. So that's part of the tree, which is the global state. So that's pretty cool. If you ever want to go and dive into the details of what actually is in the global state, you can do it using Etch. Yeah, you can actually just dive in and have a look at all of these things. It's actually I mean, how big was it? It was 287 bytes. So yeah, I mean it's pretty small, yeah, for a non-trivial amount of code, and it's got the actual the names included in there. Yeah, it'd be a lot shorter if you just used ABC and shortened names. So yeah, so it's pretty compact even for complicated code. So you can imagine a pretty complicated smart contract is probably only going to be a few K of storage, including the symbol names and stuff like that. So it's pretty compact format, and of course all content addressable. So all this is on Etch. So and of course things like smart contracts, often the same code gets used in multiple places. So Etch is just going to deduplicate all of those, and that's one of the reasons we get quite good memory size savings. Is it doesn't really matter if the code is the same; it's just going to get deduplicated, so the peers don't have to worry about storing multiple copies of the same code. So that's pretty cool. If we wanted to actually write data to Etch, there's a Etch write command. So I can just put in some convex data. Let's just put in a vector like that. Okay, and it says data saved with hash, so it's giving me back the hash of that of what it's just put in. And if I do convex etch read again, paste that in. Yeah, it comes back with the same vector. Yeah, so that's you can read and write data as you wish using these command line tools. And obviously, your regular user is not going to be doing that. Your app is just going to send in messages either to a REST API or to a binary API, or maybe it's going to directly talk to a local Etch database or something like that. But you've always got these tools that you can like dive into the really low level to look at what's going on in the data, and as I say, if you wanted to back this entire thing up, well, I can just copy the entire database file, or I can just take a dump and keep all of the encodings, and then I've got a full backup of all of this data. Now, if two people had an Etch database and you wanted or you had a backup of some old data that you wanted to import from maybe another place, then you can just import all of that data straight into your Etch database, and it just merges everything together. Absolutely zero conflicts. Never any issue doing that. You never lose data if you do that kind of merge. So it's always safe from that kind of model. So anyway, hopefully that's useful. Just give a bit of an illustration of what's going on under the hood when we talk about the data lattice and all these things that are getting moved around. Let me just switch back screens again. So a couple more questions coming up. Long-lived tape. Yeah, I mean tape's good. I mean you can store quite a bit in them. Back in the day they were pretty good storage systems. Quite low latency. I mean, it was one of those trade-offs. It was a latency between capacity, and it was the trade-off between capacity and how quickly you could get your data back. Not very good for random access, but yeah, I mean, for backup, it was great stuff. Another question. Yeah, it is really cool. Yeah, very cool. So does this mean I could write a smart contract with hashes if I knew what the line of code was underneath? No, you couldn't, and let me tell you why. If you got the hash of the code, because it's a cryptographic hash, there's no way from getting back from the hash to the underlying content. Yeah, if you could do that, then most of modern cryptography would be broken. So you can't go from hash to content. You have to have the content. On the other hand, if you knew the encoding of the encoding of the let's try and do it. Let me try and do this. Where's it? FF vector. This one here was the op. Yeah. Let me see if I can do this. I've not tried this before, but if I copy that encoding of that op that we just took a look at, it might not work if it hasn't got the tree encoding. But yeah, there we are. So I just took the encoding from Etch, put it in here, and that's gone back to the smart contract code. Yeah. So you can go from the encoding to the smart contract and the code, but you couldn't go from the hash to the code. So it's a one-way function, if you like. Could Etch storage build be a product alone? Yes. So this is a really good point. I mean, this is currently all open source tooling at the moment, but it definitely, the intention is this becomes a product that people can download and use without too much technical depth, and you could package it for enterprise. Yeah, so the data lattice is exactly what many enterprise customers might need if they're doing federated data sharing. Yeah, because this is great for sharing data. Yeah, you can transfer these edge databases and the hashes, and the replication is just sort of super clean and automatic because of the lattice technology. So I think it's a very powerful enterprise product. We still need to build it into a product, of course. So there's a cool project there for anyone in the community who wants to build a data lattice enterprise product. But exactly, that's exactly what we want to do. We want to enable that kind of capability using the data lattice. So yeah, it should be a very good product architecture. And I'm hoping that we can do some simple things like Dropbox. Decentralized services that can replace things like Dropbox or some of these Web 2 style personal storage solutions. That should be possible as well. Because remember, you can also encrypt this. I mean, I've been showing kind of the raw data, but it's also 100% possible to put encrypted data in the data lattice as well. So it doesn't matter if you send it to other people to back up; they still can't read it. That's definitely an interesting model as well. That could be open source, peer to peer, for sort of file sharing, this kind of thing. So all of that is it becomes possible. What's that at the bottom of chat? Project interested in building that kind of thing called SureStore. Yeah, I don't know too much about that project, but it's definitely, the data lattice is designed to support these kind of applications and the capabilities that you need. And I think this idea of being conflict free, this idea of being a proper lattice, is really important. Yeah, because that's what means you don't get conflicts. That's what means you don't have versioning issues, and everything gets deduplicated and it works smoothly. That is really powerful. Like, I don't know if for those of you who are programmers familiar with the software called Git and version control system, which basically was a sort of breath of fresh air in software development, because suddenly we had this really good version control system that enabled multiple versions and branching and all of these kind of interesting capabilities. And under the hood, Git is a bit like a data lattice. Yeah, it has a bunch of objects that are stored in a content addressable way with hashes. So Etch was somewhat inspired by the idea of having a sort of Git-like database for content, and the idea of having this idea that they can then be merged and branched and forked, and all of these kind of operations that you might want to do with quite big data sets potentially, is all made possible by the data lattice and by the underlying Etch store. So if you think about a sort of Git for data, you're kind of close to what the data lattice is providing. Okay, another question. For enterprises that want to use the storage system, can Convex be augmented to a private blockchain and only broadcast to their peers? So, I mean, yes. I mean, theoretically, you can use Convex in a private configuration with just a small number of collaborators, maybe on a VPN or something like that. But I do emphasize, you don't need to do that to use the data lattice. The data lattice is, it's like it's a component of Convex, but you don't have to actually run the consensus algorithm or have smart contracts or anything like that for the data lattice. You can use it completely independently, and for enterprise systems that may be a perfectly good solution. Yeah, if you trust all the participants, I would say you don't necessarily need decentralized consensus. Yeah, and Convex is designed for a public network where you don't trust everyone else. Yeah, so you need the Byzantine fault tolerance. You need global consensus. You need a global state where you can that you can verify all of these kind of things. In a private context, you don't need all of that stuff. So it may still make sense, but the data lattice alone, I think, is probably sufficiently compelling for a lot of sort of enterprise setups. And yes, you can do private data on the data lattice, and you can encrypt it. So I would say there's two levels of protection. Yeah, you can simply keep your data lattice store private and not let anyone else see it. Yeah, and then it's kind of just like a file on your disk. If no one's got access to your disk and hasn't got your passwords and your disk's encrypted, then it's actually pretty safe. So the actual etch store doesn't need to be encrypted for it to be safe, providing you keep it private and providing you don't let people read the file. But if you go on the extra level of security, then you can put the encryption obviously on the individual data within etch, and that gives you this extra level of security, which is may be useful in some contexts. So up to the user. And also, if you were to make it into a service, like something that was accessible to other people, well, you'd probably put something like a REST API on top that gives access to the data, and you can put your own then custom access controls on that API. Yeah, like, do you have to be a subscriber in order to read a database, for example? That kind of model. So when you're talking about the external interface that you present to the world, you have a lot of options, but probably a REST API with some kind of authentication and authorization would be appropriate. That's the kind of thing you would do for most enterprise systems. 2-minute warning. So yeah, we're probably going to wrap up soon. But if there's any more questions, happy to answer them. Okay, cool. Well, as always, if people are interested in this stuff, do drop by the Discord. Happy to talk about any of the funky stuff, and if people want to play with the tools and experiment with the data lattice stuff, then definitely drop by, and we can play around with some of the development software. As I say, this is still in development. I mean, etch is pretty much finished, and it's pretty solid, and it's been serving us well for 2 or 3 years now. So the underlying database is very powerful, but I think we're still building the tooling and the layers on top of that to sort of turn it into powerful products. So definitely there's good opportunities to get involved in actual building here. Question: what bits are still needed to make the data lattice live? So probably the main things I would say is we need to create a lattice REST API. So we already have the REST API for talking to Convex itself, but we would probably want another REST API for lattice nodes to talk to each other. And this is going to include stuff like replication. Yes, if I want to take a big dump of some data from the lattice, and I want to request that over HTTP, how do I do that? And those sort of protocol bits for the lattice nodes to talk to each other. You can currently do all of that manually with the tools like the command line tools that I demoed, but that's not really what you'd want in a sort of a fully automated system. So the APIs that data lattice nodes need to use to talk to each other is probably the main thing, which is just really quite a thin layer on top of etch and the lattice storage. But it is quite important to get that right, because it's protocol stuff, obviously, and you want to get protocol stuff right, otherwise changing it is unnecessary pain. So I'd say that's the main thing required to make the data lattice live. Of course, the data lattice is live in the sense that the peers already use it. It's used for peer data replication and stuff like that. But the peers are kind of doing their own protocol. So to have a separate protocol for the data lattice, I think, is important if we want to get it working as a sort of independent solution. So as I say, great opportunity for people to get involved and contribute to some of this stuff if this stuff interests you. So okay, well, hope you've all enjoyed the discussion. Thank you very much as always for all of the great questions. I've enjoyed talking about all these cool geeky topics, and see you next time. Take care. Bye for now.